use the PPT wherever it is possible and also use some Blackboard notes where I can write and show things which I wanted to describe. Okay. So, yeah, as I was asked to talk about the solid state defects in two kinds of materials. One is silicon, another one is diamond. Okay. So, silicon and diamond, there is some kind of a one to one, I would say, some kind of a resemblance is there between them. We'll see all those things one by one. Most importantly, why we have to study them, why we have to know about them. That is also very, very important question we should ask ourselves. Okay. So usually electronics people will study this semiconductor physics. Mainly the objective for them for studying semiconductor physics is all the electronics, mainly starting from diodes and then go on to come up with transistors, and various types of transistors are there. Transistors like field effect transistors, it's called FETs, and other transistors are conventional transistors like diode. Multiple diodes put together, we are going to create double junction diodes. They are like transistors like PNP, NPN transistors. Like I said, field effect transistors are another type. You can combine them, you can come up with some hybrid transistors. And in the FETs itself, there are two types like N channel field effect transistors and P channel field effect transistors. So these can be combined and form something called CMOS, means complementary metal oxide semiconductor field effect transistors. These are called. So the electronics people will study semiconductor physics to understand what kind of a material to be used to create the transistors. If they want to start with the diodes, what kind of a material to be used for the diodes, and what is the physics behind those material. From there on, they will understand more into the details and they will come up with the better manufacturing method of transistors, and then putting up transistors in a small region. They may make chips. Okay, those are like the ICE integrated chips which we have these days. They all depend on how many number of transistors we can put in a small chip. Okay. So the Moore's law says it was doubling for every 2 years, and now it is almost exhausted. Doubling is forgotten. It is exponentially increased for every 2 years, the number of transistors put in a small chip. Okay. So those are all there. But when it comes to us, the people who are getting into the quantum computing, why do we need to understand this semiconductor physics? Let's say we are not getting into the full semiconductor physics. Let's say we'll only study why the solid state defects in material like silicon or diamond is very important for us. Okay, so that is what we are going to address today. If there is any question along the way, please put it up on the chat. We will discuss. Okay, so here in my PPT, the first slide itself, I say something about the three intersection of the solid state defects in silicon PPT. What is that is, the first one is it consisting of the crystal physics, talks about crystal physics. Okay, it is in a way foundation. Having that foundation, we can immediately realize something called quantum qubits. You see now why we are going to study them, because we will be getting the quantum memory, the quantum qubits. Okay, so just like the various qubits realized being discussed throughout this module, the silicon defects and NV center defects or the diamond defects are the means for us to realize quantum qubits. So it's a application built on the foundation. Okay. And moreover, if you see the material being used here to realize the qubits is a silicon. It is a semiconductor material. The same material is being used for what? Making transistors, making advanced transistors like CMOS, which are being used for integrated chips. You see now, the moment you create a quantum qubits out of this kind of a material, it straight away becomes interconnected. It's possible to connect them. How? We are making qubits out of silicon, and already chips are being made up of silicon. So integrability means connecting them becomes straightforward. Okay. Right. I'm not changing any slides. I'm just still discussing the first slide. So it's like an industry link. So I see a question straight away here. There was a Moore's law on transistor density of the chips. Since when we broke it and started growing exponentially on transistor density in chips? Okay, so the question is since when? Exact time I can't say, because people say we are almost violated the Moore's law, because it's not doubling anymore. It's increasing more than doubling the number of transistors in a given chip. Okay, right? So you can just look into that. So it's not much connected to our quantum computing here. So we'll just like ignore that for time being. Okay, right. So let's go further. Like the next slide, what I have here for you. Okay, right. Silicon crystalline structure. It is okay. So silicon is said to be insulator. Okay. So before going there, let's understand the silicon, the atomic structure. Okay. For example, if you just take a metal or a conductor, let's say conductor. What kind of a conductor? Let's say take a copper. Okay. Consisting of what? 29 protons, atomic number, 29 electrons, which means it consisting of a nucleus having 29 protons. If you want, you can put it like inside 29, surrounded by orbits. Okay. And in each orbit, certain number of electrons were put in. It is distributed. Okay. And who distributes, how distributes? Probably nature has distributed. If you notice carefully, there are two orbits, sorry, two electrons in the first orbit, and then 8 electrons in the next orbit. So together, first and second one consumes 10 electrons. The next one is 10 are over, 10, another 18 are there in the next. You can just keep putting up just for understanding. Okay. So let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. Something like 18. And 10 plus inside the first orbit, second orbit, and the third orbit. So all of them together consumes 28 electrons. The last one lone electron is there, the copper. Now, what copper is known for is being a conductor with one unpaired electron. That is most important. So this is the most important part, is this electron is loosely held to the nucleus. You know why? So this electron, in order to see the nucleus positive charge, it has to see through the three bonds, three orbits, first, second, and third orbit. So due to this, there is a Coulombic force of attraction is there for sure. That is very, very limited, but very, very weak. because it has to go through, the force of attraction has to go through the cloud of electrons in the first, second, and third orbit. So if you see this overall setup, if you can approximate, this can be approximated as one positive charge at the nucleus, like a one proton, and outermost orbit of fourth orbit, one electron. So this is the fourth orbit. So this is what the equivalent structure of copper would look like. You know why? So the 28 electrons in the first, second, and third orbit nullified by 28 protons in the nucleus, means they become together neutral. So what electron in the fourth orbit sees is only one positive charge at the nucleus site, that is a one proton. So that is what I addressed to draw the equivalency. Now you see the force of attraction between this one proton and electron is there. Since it is too far, and moreover it has to go through electron cloud, the force of attraction, it is a very weak. So due to this, a small external motivation can easily knock the electron out of this atom. In that way, the copper atoms are easily contributes for the conduction of current in terms of abundant free electrons. Okay, so that is a known factor for the conductors. You take any other, okay, so any other conductor, if you just take silver, gold, they're all known for such a unpaired free electrons abundance. Okay, like I said, example is another example, silver and gold. Okay, why did we go on to this? To understand the conductor is, we want to know what is the like a semiconductor falls between insulator and the conductor. Okay, so conductor for sure we just saw abundance of free electron. Insulator is no abundance of free electron. Okay, means they're strongly paired to the nucleus and no electrons are freely available. Those are the insulators. There is something exists in between. They are called semiconductors. What are semiconductors? So semiconductors are something, they are not completely freely available, free electrons, or not completely strongly held electrons, something in between. Okay, to understand that, again let's take orbital structure of some kind of a semiconductors. So such semiconductors, the mostly known semiconductors are silicon and germanium. Okay, so these are highly known free electrons, semiconductors. What they are known for is, if you just take a silicon itself, again it has a nucleus, first orbit, second orbit, and third orbit. Inside the first orbit, there are two electrons. Okay, and second orbit, there will be 8 electrons. Okay, 8 electrons. Fine. So 8 electrons are there, and in the third orbit, there are 4 electrons. See, the outermost orbit has 4 electrons. Whenever electrons exist in an orbit in an even number, they are going to pair up opposite way. The spins. The spin of this one may be upspin, spin of this one will be downspin. In that way, they together would form something called upspin and downspin. Okay, two small bar magnets put together. Okay, same story for the other two. Okay, so whenever we don't have unpaired electrons, we will not able to see free possible electrons available from the element for the contribution of the current. Now, what is the equivalent structure of this silicon? Okay, just we earlier we draw, right? So first and second orbit consisting of what? 10 electrons. So those 10 electrons would be nullified by 10 proton charges of the nucleus. So for silicon, how many charges left? 4 electrons. 4 positive charges are left inside. It's about 14 protons are there. Out of 14, 10 were nullified by the outermost electron. So all the way the outermost orbit, it's called valency orbit. How many electrons will be there? 4 are there. So basically what it says 4 electrons. Okay. The nucleus consisting of 4 protons and outermost orbit consisting of 4 electrons. This is what the equivalent structure of silicon would look we had. Now, the silicon is capable of, in the outermost orbit, taking 4 more electrons. Okay, so that's why it's called the valency possibility of silicon is 8. The question is why 8? Okay, it's by nature things are like that. Okay, so a given silicon, okay, let me draw it, a given nucleus with outermost orbit. 4 electrons are available right now. So it is capable of taking 4 more electrons. Okay, from where it can take? It can accommodate what I mean. So its valency can go up to 8. Right now only 4 electrons are there. It can take another 4. Now what it can do? It can borrow 1 electron from another orbit, another atom. Okay, so what happens? Another atom may be nearby, just adjacent. So that electron can be taken or shared. Now see, whenever a sharing happens, okay, some kind of attraction between the electron of the other atom to the nucleus would happen, kind of a attraction. Similarly, electron of this one, the left one, is attracted to the nucleus of the right one. So what they form something like a covalent bond. What is that is? One silicon atom nucleus, another silicon atom nucleus get attracted with the sharing of electrons. So in this way, a given nuclei of a single silicon here is happen to satisfy one extra electron. And what else is there? It is capable of taking 3 more. Okay. So likewise, if you happen to see one silicon, okay, let me draw it smaller. One silicon can take, okay, 4 more. See, they can share. Okay, so the moment they share, wherever there is an intersection of the orbit, I'll put up shared electrons, right? Now see, now at the center, the silicon center silicon atom, you see this one, silicon at the center, it has 8 valency electrons. Now it is satisfied. It's hungry. Okay. So 8 electrons are there. Now it is done. So in this way, what happens? They are going to form a very good, this formation of a good covalent bond, which is like 4 surrounded by 4 silicon atoms surrounding one silicon atom, forms a very good covalent bond. Covalent bonds by nature very strong. Okay, so it's difficult to break the like a bond between them. It's like a chemical bond. So this is what we see, right? If you want to understand this in terms of the orbital structure, the shape of the orbit, they're going to form something called tetrahedral structure. Okay, so this is going to be tetrahedral structure in terms of solid state physics. Okay, it is also shown as sp3 hybridization, which I'll just show you what are these two things. Okay, so what is the tetrahedral structure is, it involves one s orbit. S orbit for any given electron would be a circular orbit, s orbit. And what is a p orbit? P orbit would be like some kind of a dumbbell, p orbit. So this one involves what? One s orbit, four p orbits it involves. So one s orbit, four p orbits are involved in this. Like p orbits means four surrounding silicons. So basically what it forms, it is going to form something like that. Some kind of a pyramid structure standing on the three legs. At the top, we have, okay, we are going to have another silicon. So this is the sp3 hybridization structure. We have it in our PPT. Let me show you. Okay, fine. So yes, do I have it here? No, I have it here. Okay, see, this is a sp3. What I have it here at the left. Okay, let's say I have only three PR bits, one SR bit is involved, that is going to create something called sp2 hybridization, which is a different ball game. As of now, we'll just leave it at that. Now we say this is what silicon crystalline structure. For example, if you just concentrate on these four, see, one silicon is surrounded by four more silicons. Similarly for everything, right? So this entire thing is called lattice cell. Okay, right? So what is the length of the lattice cell is represented as a lattice constant, is about 5 angstrom. Okay, for silicon structure, crystalline structure. We just discussed just now. It is a tetrahedral bonding. Four covalent bonds are formed for each silicon at the center. Okay, right? So sp3 hybridization means it involves one s orbit, four p orbits. Okay, it is represented as sp3. Okay, and one more thing, it is going to have the silicon is going to have something called indirect band gap. What is the indirect band gap is? Usually from the conduction band to the valency band. Okay, so we are going to have some energy gap, right? So the electrons, if there is electrons from the lowest orbit, if they have to jump, they need this much of energy to be supplied. So in that way, the electrons would jump by taking that energy. Okay. So, but in the case of silicon, the band structure is indirect, means something like that. Okay. Right. Valency and conduction bands are separated by some kind of a dislocation. So in order to jump, they can't directly jump. They have to go through some kind of a lateral transition, apart from jumping directly. Okay. So this is indirect band structure. Indirect band structure. Okay. It's like electron has to travel up and then take left. Okay. Right. So yeah, in sp3, how the carbon is came to the structure. Okay. Somebody was asking here, right? So this is a center silicon, right? So in fact, this is used to represent CH3, okay, tetrahedral structure, sorry, CH4, methane, right? So their center carbon is there for hydrogens are there. That's why people used. So C stands for, let's say, center one. Okay. So you can think in that fashion if you are not comfortable in saying as a carbon. Okay. So basically, silicon is consisting of such a nice packed structure. Band gap is 1.12 electron volt indirect. Okay. And inside this, the electrons mobility is represented with the mu e. And there is something called holes can be formed. We'll come to that. What is that is, if you notice this, the structure of silicon, okay, what it can happen is sometimes the shared electron can just go out and move freely. Okay, right? So whenever the shared electron just comes out, what it forms is, electron comes out, it forms a hole. Okay, so whenever the hole is formed, 1 minute, right? So just a minute. Whenever a hole is formed, what happens is, just a minute. Yeah. So whenever a hole is formed, electron comes out. A positive charge exists at the wherever the electron was earlier located. So this is how there are positive vacant spot and the electrons are created in the silicon material. If they come on their own, it's going to form something called intrinsic semiconductors. The question is, when this, earlier I said electrons were strongly held in the form of covalent bond, how come they can come out? Please remember, this strong structure would exist something around 25 degrees Celsius. By any means, if the temperature of the silicon material goes high, in that case, what happens? The bond can be broken at some point and the electrons can come out. So in this way, if you supply the external means some kind of energy, knock the electron out. In that way, what we can do, we can create the defect in the system, increase the temperature, make the electrons to go out, and we can form the defect in the system. So what happens when the defect is formed? You see, you can draw the figure again, just for understanding. Okay, so shared electrons are there. Okay, but at some point there is a vacant spot. Okay, wherever that halo region is a hole and which is positive charge, and the electron came from the halo region would roam around. Okay, this is a positive charge. So this roaming around, let's say the heating would create inside a silicon lot of electrons. So lot of electrons are created, then it is forming something called n-type semiconductor. Okay, so it's by heating you are forming same number of holes, same number of electrons. How can you have n-type semiconductors, right? So intrinsic semiconductors, we cannot make them a particular type, n-type or a p-type. For that, artificially we make something. Okay, we are trying to add extra electrons from external means. Okay, for that, what people thought is, people thought, please remove one of the silicon. Okay, remove one silicon and add one external atom. Let's say there are atoms, two types of atoms are called. One is pentavalent. Okay, I'll tell you what is pentavalent. Another one is trivalent. Okay, pentavalent are the atoms known for having 5 valency electrons in their outermost orbit. And trivalent are the one having 3 valency electrons in their outermost orbit. See, this nature-wise, these pentavalent atoms are very close to the silicon kind of a behavior, and trivalent also very close to silicon kind of a behavior. Now, what we will do? Let's take atoms like okay, atoms like aluminum, okay, or boron, or gallium. So, what we will do? These things by nature trivalent. Okay, so what they will do, they extract the electrons into them to make the trivalent to become 4 electrons in their structure. So in that way, what they will do, they are going to create holes in the system. Okay, so those are trivalent atoms. Okay, in that way we can create the extrinsic semiconductor having abundant positive holes. They create positive holes when we dope with them. Okay, at the same time you take arsenic, okay, or for example antimony phosphorus. If you take this, these are having 5 electrons in their valency orbit, so they don't need 5, they only need 4 to share with the silicon which is being replaced with. So what they will do, they will use all the 4 electrons, okay, and the 5th electron they leave it outside. So the 5th electron will be contributing as negative charges responsible for conduction. In that way, what we are doing, we are going to create N-type semiconductors, extrinsic semiconductors. So the pentavalent are known for creating N-type semiconductors. Trivalent were known for P-type semiconductors, extrinsic semiconductors. Okay, so this is how the defects are going to create the interesting behavior in the case of silicon. Okay, so let's go back to our PPT. Okay, now, so the question here is, there is some order. What is that order is? The long range periodic order of the diamond cubic lattice gives rise to band structure and carrier transport and quantum coherence. Okay, so any disruption to this order, which is a defect, creates a localized electronic states that fundamentally alter the device and quantum behavior. Just like a diamond having nice structure, in a similar fashion, silicon will have such a structure. By any means, if you dope with a phosphorus, which is a pentavalent, okay, sorry, which is a phosphorus is a pentavalent. You dope with a pentavalent, abundant free electrons are going to be added. Okay, so those are going to create some kind of a interesting quantum behavior by altering the band structure of that material. Not only pentavalent, if you dope with the boron kind of a trivalent atoms, in that case they need extra because they're only coming up with 3 electrons. They need 4 valency electrons by nature. They're very close to the silicon kind of a behavior. So what they do, they borrow from nearby silicon. In that way, the nearby silicon was made to shortage of their valency 8 electrons. So in that way, the negative charges or positive charges are created. Okay, so please see, silicon can become extrinsic p-type or n-type. By becoming, it is going to create some interesting quantum behavior. Okay, right. So let's see what else we have here. We can have not only this, we can have different kind of defects. One is called point defects, planar defects, the line defects, and the volume defects. Okay. So just by replacing with a different the external means like boron or phosphorus, that is one way of creating defects. The other way of creating defects is point. I just mention whatever here. Okay, point defects are vacancies. These are called interstitials. Okay, substitution with the impurities, which can be confined to one or few lattice sites. Most importantly, for electronic and quantum applications, this is a very good means. Okay, so phosphorus in silicon is a pentavalent, abundant free electrons, n-type semiconductor will be made. Okay, and vacancies can be created with the trivalent. So this is called Frenkel pair. Okay, so this is some just now whatever defect which we talked about. Another one is planar defects. Okay, right? What is done here is the grain boundaries are created. Okay, you can create a stacking faults. The way you are stacking, you are not properly stacking. Okay. Okay, there is a question here. This doping creates a p-type and n-type transistor. What is the quantum in this? Oh, very good. Okay. So the again transistor, what is the quantum property in this? Not clear. We'll come to that. We are coming to the quantumness. Okay. And the question what you asked is absolutely right. What is a quantum? What is quantum matters to us? What is a quantum matters to us is creating a qubit out of it. Okay. So we are just trying to go there by building from here. Okay. Since the topic is talking about the solid state defects in the system, okay, how these defects are going to allow us to realize the quantum qubits. So to address that, we are starting from seeing various kinds of defects exist in the silicon. Okay, right? So the planar defects is another one. The way you like you stack the lattices, right? So that if there is a defect in that, that may cause some problem. Okay. So this is very critical in the case of polycrystalline silicon, less common in single crystal device wafers. Okay. Not much matters for us when it comes to qubits. Okay. The next one is line defects. Okay. So it's like edge dislocation. It's proper having nice lattice, it will not going to have. There is some kind of a dislocation at the edges. Another one is volume defects. Okay, so it can be voids. Okay, so we need supposed to have certain structures with a nicely packed silicons, but the packing itself misses at some point. Some kind of a void is created. So that is going to be volume defects. Okay. So these are going to form some implantation, damage, annealing in the system. Right. So yeah, what matters for us more is how are we going to utilize these defects in realizing the qubits. Okay. Right. So again, this is described in terms of detailing how the phosphorus is going to contribute. Okay, it's a being pentavalent, extra electron is being contributed, and boron by nature it is a trivalent, it accepts electron from somewhere around. In that way it creates a holes. So from that context it is explained here. Okay, now okay, so the details in terms of physics is explained, defect reactions, doping in silicon. Okay, so when it comes to us, what is a quantumness for us? Okay, let's keep this point as well. Okay, so let me go somewhere. People are asking. Yeah, yeah. So why defects can be qubits? Okay. So in a perfect crystals, if you see, electrons are delocalized into block band states. Impossible to individually address them. and defects create isolated atom-like quantum states inside the silicon lattice that can be controlled. Okay, right? To understand this, what we have to see is, first of all, what is the band structure of the N type and what is the band structure of P type semiconductors. That we'll understand. Okay, so if you understand them, what happens is you can appreciate how exactly we are going to realize qubit out of it. Okay, fine. Now let's take N-type semiconductor material. What it's consisting of? Freely available. More free electrons are available. Okay, let me put them. They are the majority carriers. Means probably silicon might have been doped with pentavalent. So due to that, more free electrons are there. Let's connect the left hand end to positive terminal, right hand end to the negative terminal. What happens here? All the electrons were attracted towards the positive side connected terminal. And electrons were obviously rejected or reflected, deviated, go to the, sorry, electrons, the positive charges would go to the other side. So positive charges are very few, majority are electrons. Okay. Now, what is this band structure would look like? Now, inside a silicon, if you just see, usually what we see one spherical electron, one ground state orbit, first excited state, and second excited, and third excited, something like that we will see. But since it is surrounded by many other nuclei, not every electron says same kind of an orbital structure, orbit structure. If I just take one particular electron, it says this kind of orbit. First, second, third, and fourth. One of the electrons is like this. Another electron is slightly different. Okay. If I want to address or represent the electrons and their ground state energy, first orbit energy, all the electrons in the first orbit, if I want to address, they are going to form a band of orbits. Similarly, the first excited state. Similarly, the second. Similarly, third. This is where the band is going to be formed. Okay. Now, we are talking about N-type. N-type means more free electrons. How they are formed? Probably many electrons are there in the outermost orbit with most freely available electrons. So which means the excited state, the most excited state, the outermost orbit would be having electrons freely available, many electrons. Okay, right? And probably where the electrons have come up, in terms of silicon I am talking about, some electrons were jumped from the valency orbit, which is valency, to the conduction band. Okay, valency band and the conduction band. So from individual silicon, one electron had jumped and go on to occupy the conduction band. Only one electron I am showing where the other electrons are coming. They may be coming from the doped pentavalent atoms. I'm sorry, pentavalent atoms contributed further. This is the band structure. Energy band structure would look like for N-type. Here, majority are electrons. At the same time, if you just take a P-type, what you do is you take P-type material, which is being doped with trivalent atoms, means more holes are there in that particular material. Few electrons are also there, not much. Now again, let's say you connect to a battery, external battery. You know what happens? Positive charges were repelled and electrons were attracted. Less number of electrons are there. What happens is electrons will hop from one hole to other hole and then travel. The positive charge is what it appears to me like traveling towards the right. Okay. So this is how some current is conducted through this p-type material. Now, if you want to draw the band structure, what I'll do, I'll just try to see for given electron, one single electron in a silicon, what would be its orbit? It's a ground state orbit, first excited state, third excited state, and the next state. Okay. Since not every electron sees the same kind of orbit because it is surrounded by many charges, their orbits slightly deviated from each other. So again, here also there is a band is formed. Ground state, this is ground, excited, second excited, and third excited. So this is a conduction band, valency band. Okay. Now, as we by nature, the p-type material is going to have abundant positive charges. Means in the conduction band will have very few electrons. But the holes are more in the valency band. Okay, these are holes. How holes are going to contribute the current? By electrons hopping from one hole to other hole. In that way, they are going to contribute through holes to the current. So this is a p-type band gap for us. So between valency band, conduction band, there is some kind of a band gap exists. Here also exists. So now having this band structure, we can start understanding. Okay. So through the doping, in a way it is called defect, we can create a quantum qubit. Okay. Right. So how it can be created is we can introduce quantized levels in the band gap. The ground state and the first excited states form natural 0 and 1 qubit basis, just like an artificial atom inside a silicon. Okay. So like I said, you can pick the band structures here. Within that band structure, we can confine to two of the levels with some specific energy separation. From there itself, we can realize a qubit out of it. Okay, right? So how we can do a controllability? Controllability is we can use the spin states. We can make electrons by nature going to have a spin, and they are existing in the spin of a nuclei. Okay, and by having the interaction between spins, we can manipulate with a very good precision. Okay, so the nucleus itself is having its own spin. It's like a small bar magnet. So those are magnetic fields are there. So within those magnetic field lines, the electron is also there. Now, electron is seeing a particular magnetic field from the nucleus. Now, what we do from external means we can induce a magnetic field. Okay, so we can just manipulate the field of interaction between the nuclei and the electron from external means. So this is going to create what? Zeeman splitting. Okay, so using magnetic field, we can just create the splitting. Let's say if you just to take any one electrons of ground state and the excited state. Okay, so electron minds its own spin. It can be up spin or a down spin in this particular states. Now, when I apply external magnetic field, what happens? The ground state may going to have two possible ground states. It's basically called hyperfine splitting. Okay, right? Here there are two ground states. Similarly, we can have two excited states. So the presence of external magnetic field creates such a thing. Now, if the electron is by nature in the ground state earlier, the moment magnetic field is applied, electron may get occupied either here or there. Okay, right? So this is how we are going to see the involvement of external magnetic field by creating hyperfine splitting. Okay, so the controllability of where the electron could be placed in which particular state is all about the external magnetic field. Okay, right? So you can do the same thing by using magnet electric field also. That is called Larber splitting. Okay, this is using magnetic field is a Siemens splitting. To do it, you may not be needing a serious amount of electric field or magnetic field. You can just use a simple microwave pulse sequence which can come up with a small electric and magnetic field. They themselves can put the electron to hop between the ground and excited state continuously. It's just like a Rabi oscillations. So electron can go back and forth using such a thing. In that way, we are going to create a superposition state. Let's say you call it as 0 minus. This is a 0 plus. Let's say this is 1 minus. So in this way, between 0 minus to 1 minus, we can create a superposition state. So 1, 0 minus plus beta 1 minus. Okay. And this is a Rabi rotations or Rabi oscillations. So how much oscillation should happen? Okay, what kind of a change has to undergo? Those are all gate voltages or exchange coupling. How much coupling has to happen between incident microwave pulse to the qubit which we are realizing out of this a silicon electron inside this silicon material in terms of its defect is going to be addressed. Okay. Now, how can I represent in terms of mathematics? Okay. So, a donor qubits can be realized. For example, pentavalent atoms are going to contribute one extra electron. That electron is going to exist in particular field. So, in general, what we do, we are going to represent a system of an electron, for example, a qubit, in terms of its surrounding and its surrounding environment plus the system itself. So usually we represent in terms of Hamiltonian, simplified Hamiltonian. Okay. So where in this Hamiltonian, if you carefully see, there is a coupling factor is there, A, right? And applied magnetic field is there, B. Okay. And mu B is a Bohr magneton. Magneton means how much magnetic field is generated out of a single electron being rotating on its own axis, or let's say it is rotating in presence of external magnetic field. Okay, what is this Hamiltonian? Please explain. Okay, okay. So let's quickly explain what is the Hamiltonian for you people. For the electronics people, probably sorry, for computer science people, probably you will be not knowing it. Okay, just I'll start from very simple concept and then we'll start to build from there. Okay, for example, if you just take a simple pendulum, okay, it is having length L, a metal. It is, let's say I give small amplitude, it oscillates. Okay, right? So this is a simple pendulum, right? This is also equivalent to something called spring mass system. You take a mass m on surface let's say a frictionless surface, okay, and let's say spring is there with some spring constant. If I dislodge the location by some x mass, it is going to oscillate, just like a simple pendulum oscillating. Now, to study this dynamics of the system, we can write some external force F is applied, which is going to create some acceleration in the system. This is a Newton's second law for you. F external is equal to ma. Okay. Now, whatever external force you are going to execute, that is going to create some restoring force in the spring. That is what, you can't stretch the spring forever. After that, spring will exert a force onto you, so that you can't stretch it anymore. You have to leave it. So spring will try to come back. So the external force would become equal to the restoring force. Okay. So by the way, the restoring force is equal to this minus of K, the spring constant, into how much extension you have applied. So K is a spring constant. It is a minus sign represents exactly opposite to the external force. The spring constant creates a restoring force. So this is a spring constant system for you. Now let's say I ask you a question. What is the oscillation frequency? With what frequency this system is going to oscillate? How long these oscillations are going to sustain? If I ask such a question, you have to study the dynamics of the system. Okay. So for that, what you are going to do, you are going to study this dynamical equation F is equal to ma. What is that? F is equal to ma is mass into second order derivative of position with respect to time. You are going to get what? Second order differential equation. You replace F external in terms of minus kx. What you are going to get is second order differential equation in, okay. So this is what you are going to get. So this is second order linear differential equation. So this differential equation is going to have solutions of sinusoidal solutions. Okay, right? The solutions are sinusoidal, which are oscillatory. Okay, so with what frequency they oscillate? Omega is square root of k by m. Okay, whatever the spring constant is there, sorry, omega t. Okay, so whatever is the spring constant is there, that will dictate with what frequency it should oscillate. Even the mass also dictates. Okay, this is how you are going to understand how the spring constant system is going to oscillate. Similarly, how pendulum is going to oscillate also you are going to calculate. But the question here is, where is spring constant here? I don't have a spring constant in the spring, in the simple pendulum. No. Even in the simple pendulum case also, there is a restoring force. What is that restoring force? Is when I leave the system to the external, like extreme direction, after some time oscillates and tries to come back. What is tries to come back? It's due to the gravitational force, it tries to come back. So from the gravitational force, it's going to create the spring constant or restoring force. Okay. So to understand such systems where we can't explicitly write down the internal spring constant and other things, what people thought is people are trying to write the total system energy in terms of some total energy is equal to kinetic energy plus potential energy. In this case, what is the kinetic energy? Half mv square. What is the potential energy? Potential energy means you can, let's say this is your ground. From the ground, if you are going to raise the height, or if you just take a reference point as a pivotal point, from there you are going to raise it at some height, sorry, move it, so you can represent that as a potential energy. So usually mass into gravity into some height. mgh. Okay, so this is the total energy of the system. So from this point, you have to find out what is the oscillations of the system, how it will oscillate. Okay, so why we are bringing such a classical example is, you see, when I talk about the nucleus surrounded by electron, electron is revolving about the nucleus. It is just like oscillate, like making oscillations. So which means everything at a quantum level is like a small pendulum. They call it as a simple harmonic system. Means it picks a steady state point. About the steady state point, it keeps oscillate. Means just like a pendulum, about a steady state point, it is making oscillations. To study that at a quantum level, what you do, instead of writing a total energy of the system, you are going to write Hamiltonian of the system in operator form. Operator form in the sense, some kind of a tool which tells me by using it, I can measure something. Let's say operator means just like a thermometer which operates on a patient, gives me temperature of the patient. So the total energy written in terms of operator Hamiltonian, where kinetic energy operator plus potential energy operator is there. So you can make this into some kind of a matrix. Okay, that matrix, for example, for a single electron in an outermost orbit in presence of a nucleus is going to have, let's say, 2 by 2 Hamiltonian, 2 by 2 matrix Hamiltonian. Now, by nature, the Hamiltonian is a 2 by 2 matrix. It can have eigenvectors E1 with the corresponding eigenvalue E1, capital E1. Okay, so this is eigenvalue equation. Just by finding eigenvectors of the system and eigenvalues of the system, you can find what are the possible energy states for this electron, with what energy those states can exist. And system may be doing oscillation between those orbits. For example, here in this case, this is like E1 and the next one is E2. So the electron may do hopping between E1 and E2, where if I supply the energy from external means, it may go to the highest energy state. After some time, it emits it and comes back to the old state and does such kind of oscillations. So this is how I am going to create a superposition state. Okay. So how exactly the superposition state is going to be created? Between what states the superposition state is going to be created? Okay, how much external environment means external energy is being supplied, all those things are captured inside the Hamiltonian. Hamiltonian means kinetic energy, means the electron moving back and forth. Potential energy means it is existing in the environment of nuclei, electric and magnetic fields, and external photons, some kind of energy coming in, that is also captured in the potential energy, or let's say some kind of interaction Hamiltonian. Okay, so the Hamiltonian plays a very, very important role when understanding a system at a quantum level. So it's very important to write what is the Hamiltonian of the system for me whenever I study a quantum system. Let's say a qubit or an electron itself, I can represent using the Hamiltonian. Okay, so just to understanding in a classical picture, we always bound to see things at a classical level. Hamiltonian, you can think it as some kind of a kinetic energy plus some potential energy. Okay, so kinetic energy with which system is doing dynamics, potential energy with which system is existing in the neighborhood. Okay, so that is what we have it for you here. Now, for my qubit realized out of silicon defect, what is the corresponding kinetic energy and potential energy if I have to write down? It's consisting of such a Hamiltonian. Okay, right? So the Bohr magneton, probably the magnetic magneton of the nucleus in which the electron is existing. Okay, and it's this lines orbits may get split with some value depending on what kind of a coupling it is having with the external magnetic field. See, this Bohr magneton probably comes from the nucleus and the external magnetic field is there, okay, and some G factor is there, like some kind of a coupling factor, another kind of a coupling factor between the external magnetic field and the system magnetic Bohr magneton, okay, and SZ is a spin part, okay, spin magnetic moment, and for the electron also there is some spin. So in this way we are going to represent the entire system in terms of the Hamiltonian. So you have to find, if it becomes some kind of a matrix, you can find the eigenvalues and eigenvectors of this matrix. From there we can understand what are the possible energy states can exist for such a quantum system. And is it possible to make the system do hopping between these two states, any two particular states? That also can be understood from here. Okay. So the encoding here, if I want to do, how I am going to do encoding? I can make the encoding in such a way electron can exist in the upspin or a downspin. Okay. So I can say there is downspin, there is upspin. These are separated by some energy. Okay. Right, so the electron may become downspin or upspin continuously, just like going from ground and excited state in the orbital way. Okay, so here, what is the the lifetime of such a superposition? It is in milliseconds. For example, for the electron spin qubit. Okay, at the same time, we can realize spin qubit with the nucleus also. There, the lifetime could be, oscillations lifetime could be few hours. Okay, right? It can be used as a memory qubit. The first one can be used as a gate qubit, fast gates. Okay, so coming back to what is T1 and T2, people may ask. Okay, for the sake of that, let me explain. Let's say I have a quantum state realized with a ground and excited state. Okay, so this is ground and excited. If a given electron is excited, it stays there, excited state, for the lifetime of 1 microsecond. If it decays even before that, means the T1 got decayed to smaller value. So this is very important to have a required superposition state. Means electron doing hopping between ground and excited state continuously with some particular frequency. After some time, if I supply some bunch of energy in terms of some pulse of photons, okay, photon pulse energy comes and puts the electron in the superposition. After some time, this pulse is gone, the superposition is lost. If I draw the time versus the oscillations of ground and excited, what I see, oscillations existing, after some time they decay. So I will have some lifetime for the oscillation to exist, that is a T2. Okay, T1 is excited state lifetime for a given qubit, and T2 is the lifetime of the oscillations. So we have, in our case, if I realize a qubit out of electron inside a silicon donor, that can be few millisecond time superposition state, and if it is a nucleus, it's a very good few hours. Okay, minimum up to hours we can have the lifetime. So which means I can realize a memory out of it, quantum memory. Okay, so why silicon is exceptional for quantum qubit? There are so many things. It has, I can have isotopes I can use. I can have pure silicon, which can be used for memory. Okay, we can have very good coherence times. Okay, 1 millisecond per electron. Okay, and 30 seconds, like starting from 30 seconds for a nuclear spin. Okay, and it's a compatibility with existing electronics like CMOS transistors. Okay, you can realize electrical gate control using microwave pulses. Okay, so not only that, there are other gate voltages we can use at nanometer scale electrodes, and we can realize the gates. Okay, so that's why this is an exceptional means to realize the qubits. That's why people are working on that. Okay, so these are types of silicon defects in qubits. So uh, you can just go through it. Okay, right, quantum operations. So we'll just skip for time being now. Let's see. Yeah, so let's summarize. We have to go to the other part also, the NV center defects. Okay, silicon defects is from physics to quantum computing, depending on the order crystal. Okay, depending on the doping, we can create qubits out of it. So ideal for qubit host silicon, and defects can be controlled with external electric fields, and we can realize artificial atoms. What are the artificial atoms means? In transmon case, LCR circuits can be used to realize artificial atoms. Here also, we can realize from the doped band structure, we can realize the artificial atom. Okay. So this is a very good bridge to quantum industry, because silicon donor qubits use the same fabrication infrastructure as the classical chips, which can lead to a quantum at scale. Okay, scaling can be easily possible. You can have hybrid systems. Qubits can be realized using silicon defects connected through another silicon defects through some quantum chips made up of silicon FETs, CMOS FETs. Okay, so this is how the scaling can be possible. Fine. So we'll just take a quick 5 minutes break. After that, we'll come back and discuss about NV centers, NV defects or diamond defects. Okay. Okay, welcome back everyone. Yeah, I see a couple of questions here by AK Jaji. What will the delta Hamiltonian represent? So I have not used delta Hamiltonian anywhere in the slide. The where I used a delta is to show the energy band gap, delta E. Delta E may stand for energy band gap between valence and conduction band. Okay. If there is any delta Hamiltonian mentioned, that will be like the perturbation to the system. Means Hamiltonians usually comes with the internal Hamiltonian plus some delta Hamiltonian. So this is like some external means which may affect the system, comes into the system and disturb the system. Let's say system is stable with a delta H external coming in and disturb the system slightly. It's like I take a pendulum and move it to the extreme end and leave it. So delta H could be something like external disturbance. Okay. In that way, I perturb the system, is disturb the system and see how it behaves for the external motivation. Okay. Right. Another question. Does the change in polarization of the light lead to change in the Hamiltonian or energy? Very good question. Okay. So, what is the polarization for the light for us? For example, if I just take electromagnetic wave, okay. So, if it, let's say, it's propagating along the z-axis, so electric field, let's say, electric field vector is oscillating like this, okay, and magnetic field vector is probably oscillating in the horizontal, right? So, magnetic field vector probably along the x-axis, okay, omega t minus kz, and electric field is represented as E naught y-axis, again traveling along the z-axis, positive z-axis. Okay, this is the electromagnetic field for you, EM wave. And see, electric field vector is oscillating its strength along the y-axis. It is just like initially it is like this, later it just decreases and it increases in the negative direction. Okay, likewise it oscillates. This is what the oscillations of electric field for us in the y direction. Now the question you are asking is, does the change in the polarization of the light lead to change in the Hamiltonian? Okay, right? So the oscillatory direction, let's say it is along the y right now. You move it to, let's say, x direction. Accordingly, magnetic field also changes it because electromagnetic wave are always perpendicular to each other. They just move. So if you are talking in the perspective of only the electric field only, usually we do it. The change in the polarization from one direction to other direction, okay, may induce a change in the system, definitely. You know why? If the system is meant to only respond to a particular kind of electric field, okay, electric field oscillation. In that case, if the system of material only respond to the y oscillations, okay, it doesn't respond to the x oscillations. In that case, you know what happens? Change in the polarization is going to change the Hamiltonian of the entire system, where electric field oscillation going from y to x may not create any effect on the system because the system is not going to see that x direction oscillations. I'll tell you what I mean. Okay, you just take a polarized field along the vertical plane. So this is what electromagnetic field having confined to a vertical plane. Now if I have a Polaroid, okay, Polaroid, whose crystallographic axis is horizontal crystallographic axis. Okay. Now this polarized field, if it tries to goes to this material, it will not go, because this Polaroid is meant to respond to the polarized field, which is only along the horizontal direction, but the electric field here is oscillatory on vertical direction, so there is no light comes out, which means no effect is created by this vertical polarization. It was, let's say, earlier along the x direction. If I send the horizontal electric field oscillations through this polaroid, definitely that time I will see, for example, if I have horizontal electric fields, now I have a polaroid, same polaroid, crystallographic axis is horizontal. In this case, yes, I see light being transmitted. How it is being transmitted? The atoms inside this polarizer respond to this horizontal polarizations, and then they excite and they emit. After some time, the emitted light, I see exactly the same polarization. Okay. So when I am talking, this is a classical way of seeing, means macroscopic level of seeing things. But if you talk in terms of single qubit, in that case, yes, making a change in the polarization may make a vast difference in the system. Okay, definitely the Hamiltonian is going to change, because the Hamiltonian you are representing from the electric field. If you quantize the system electromagnetic way, so initially the Hamiltonian consisting of kinetic energy and potential energy of the system. If you quantize that, what happens? The Hamiltonian is going to become a simple quantized Hamiltonian like this, where creation and annihilation operators are there in the system. Okay, so in this case, we will not be able to see the polarization of the system as such. Okay, right? But in our case, what was I was representing for a single qubit, for example, in the case of silicon, yes, it matters, because the oscillatory field direction also matters, how the silicon is going to see that input field oscillations or input field direction. Okay, so we need to see specifically, according to that we have to answer this particular question. Okay, fine. So let's get back to the next part. I hope I answered your question. Okay, right. So just like in the silicon, we can have defects also in the case of diamond material. Okay, so you were saying it is not contradicts as Hamiltonian is energy, which is directionless. No, yeah, Hamiltonian is going to see, like, for understanding, for the sake of understanding, I'm just telling you Hamiltonian is like kind of a energy. But when you go to the quantum level, it is some kind of a tool, a probe deals with the energy system and its internal energy, its external energy, and its surrounding. Everything is there. Okay, its units is just the energy units, but it is not total energy. Okay, so you can't see, just like a macroscopic world. In the macroscopic world, we see total energy of the system is some joules. Okay, right? It's acting in a particular direction. Kinetic energy is in a particular direction, it is there. Potential energy in a particular direction, it is there. It is not in the case of quantum level. Okay, so that is how we can clarify the things of this contradiction, whatever you are feeling at this point. Okay, fine. So let's go further. NV centers in diamond, just like the nice packed structure which we had in the case of silicon. Diamond is known to have such structure. Okay, so diamond exists in three forms, you know. One is graphite. Okay, another one is diamond itself. Last one is graphene. Okay, right? So graphene is, in a way, is an atomic level. If you just take a slice, a nice thin film, that is graphene. Okay, from graphite we can take it out, it becomes a graphene. So most important thing is diamond. Just tetrahedral structure what we had earlier, we discussed for silicon. Same thing is here for the carbon in the diamond. Okay, so we can realize a single qubit out of it. Interestingly, we can realize a room temperature qubit. Okay, and we can read the state of that qubit using some light. Okay, we can read the superposition state using the light. And most importantly, how is this one qubit is realized is we create a defect in the system, and that defect is going to create a spin qubit state. Means the system is going to exist in two spin states, upspin and downspin, and it is maybe oscillatory between those two spin states. In that way we can realize a qubit. Okay, so let's see how exactly it is being done. Okay, again, if you compare diamond versus silicon, okay, band gap and the structure, you see structure both are cubic silicon, and if at all, if there is any energy band gap exists between their valency and conduction band, so that is about 1.12 electron volt for silicon and 5.5 electron volt, very wide for the diamond. Okay, so both are sp3 hybridized, means the covalent structure they form with 1s 3p orbitals. Okay, and they are going to have a thermal conductivity for sure. They heat, when you heat it will conduct. And Qs is silicon was known to use for transistors, and NVs, the diamond is used nowadays for creating quantum defects. From the defects you can realize a qubits. How it is done is just like a doping. You take a nice cubical structure of a diamond made up of carbons, okay, nicely packed. You remove, say, three carbons were removed. Okay, so at the one of the carbon location place, you put a nitrogen. You dope with the nitrogen. Okay, so when you dope with the nitrogen, nitrogen by nature, looking at their size, the proton number of protons inside, and the electrons very close to the carbon, not exactly but very close, it can come and occupy the carbon place wherever it is a vacancy. So deliberately what we can do, we have removed three carbons, we only dope with one nitrogen. So what happens? One nitrogen, another vacant part of a carbon together can form something called nitrogen vacancy defect or nitrogen vacancy center. Now, if you notice, this NV center can exist in various energy states or various quantum states. Okay, so due to this quantumness, the electron in this, one of the electron of this NV center, okay, what it can consisting is it can going to have influenced by the magnetic field of the nitrogen. Okay, right, and it is something like a nucleus magnetic moment and the one electron magnetic moment together are going to interact. They are going to create some kind of a coupling electron magnetic field, nucleus magnetic field, are two bar magnets, nucleus bar magnet, and electron bar magnet. So that is some kind of a coupling is taken place. That coupling is controlled by all the surrounding nuclei of the carbon. So, so it is surrounded by many carbons for sure. But one thing is the electron in this NV center would see the magnetic field due to the nuclei. Okay. So in general, that the state of the system may have one orbit, ground state, and one excited state. Okay. So let's say this is an electron. So electron can go back and forth between these two states. Okay. Now, what happens? By any means, if there is some external field is also coming into the picture, means this NV center, which is hosted in this diamond, is surrounded by some external magnetic field. In that case, what happens? External magnetic field can split the ground state single orbit to two excited state orbits. Sorry, two ground state orbits like this, hyperfine. Similarly, there is a hyperfine splitting here. Okay. So the splitting would happen due to the external magnetic field. External magnetic field. Or even electric field, by the way. So this NV center is so sensitive to the external magnetic field. Initially, it may have the ground state and excited state for a given electron in the NV center. The moment the external magnetic field or electric field comes in, the splitting would happen for a given orbit into hyperfine levels. So due to that, what happens? The system is no more confined to just two orbits. It may be have a possibility of existing in various possible states on the hyperfine levels. Okay. So especially the NV center is very sensitive to the external magnetic field. How sensitive it is, even you can have the change in the magnetic field from tissue level, human tissue level, one cell to other cell, whatever is the magnetic field, if there is any change in the magnetic field from one cell to other cell, even that change in the cell would cause such a hyperfine splitting. Okay. So that was people were using to realize sensors out of NV centers. Okay. So they call it NV sensing, NV center, NV vacancy sensing, which is in the medical field, it is going to make a vast difference. Okay. Right. So I was talking about what are the possible different states for this NV centers. Okay. We need nitrogen atom inside a lattice of carbon where carbon is replaced by one of the nitrogen and we deliberately let one vacant part. Together they are going to create NV complex. Okay. So this can exist in neutral states like no charge. Overall, the dipole NV, nitrogen vacancy center, may have no charge, neutral charge. That is one of the quantum states. Okay. Right. It may have sometime negatively charged state. Depending on acquiring electrons available around, it can acquire that electron and in that way it can form NV negative. Okay. So at a given point it may exist in NV0 or NV negative. Right. So that will lead us to realize a qubit out of it. Okay. How it is possible is 5 electrons in the defect complex in the NV0 case. Okay. 6 electrons in the NV negative. See, one extra electron is taken from surroundings, where 2 come from vacancy carbons, okay, 1 from trapped from the donor. Okay, right? So this is how. So one nitrogen is surrounded by 4 more carbons, right? So in this way, you can have the NV negative coming in the charge state. Okay. So yeah, the band structure just we had earlier. Okay, so let me show you the band structure. Okay, so this is let me show you 1 minute. Just want to show you NV sensing. Yeah. Yes. See, this is a 1 minute. So this is here. The transition states are between E to A, which are about 1000 nanometer separation. In terms of wavelengths, the energy separation is mentioned. Okay, right? So now, because of the external magnetic field, the ground state E is split into 3 ground states, and excited state A is split into again 3 excited states. Okay, so how it is splitting and what should be the representation for the ground state? We know for any electron inside an atom, it is going to be represented by the quantum numbers. There is something called spin quantum number. Okay, angular angular spin quantum number. Okay, there are various quantum numbers. In a simple manner, there is a spin quantum number. So whenever the splitting happens into the 3 states for the ground, so each possible orbit is represented by the spin quantum number. The MS is spin quantum number is 0 means the electron is confined to the lowest level. And the MS can be plus and minus 1. MS plus 1 means in the ground state itself, one of the excited. In the ground state itself, there are 3 states, right? MS0 stands for all the way down. MS minus 1 stands for the mid one. MS plus 1 stands for all the way top. Now you see, even inside the ground state, there is a separation. Okay, where the separation is about 2.87 gigahertz. So there is an individual transition in the ground state itself whenever the hyperfine splitting happens. Similarly, the excited state also going to have hyperfine splitting where the separation is more or less very close to whatever ground state we are having here. Now, what is most important is by any means, if there is a ground state electron before the hyperfine splitting, once the hyperfine splitting happens, if the electron falls to the hyperfine splitting levels, we never know where it exactly falls. Okay, sometimes it may fall to all the way ground, sometimes it may fall into the MS plus minus 1 states. Okay, fine. What is most important is, let's say for the time being it falls to MS0. Okay, the system falls to MS0. It's a qubit system I'm talking about. It falls to MS0. Now, if I supply energy of green light, where electron can travel from MS0 to all the way MS plus or minus 1 of the excited state, E2. Okay, right? So E2, there are 3 possibilities, MS0 plus MS plus or minus 1. So if the input energy 532 nanometer green color light is applied, so electron may jump from all the way ground to the excited state. You know, internally it may decay to the MS0 state at the excited, and then it will decay later to the ground state by emitting not the green light, it will emit this time the red light. Okay, so this is how the response of green light shown by the NV center in general. Okay, but if you say, if I don't have external magnetic field, it is simply 1E transition of electron from one E to one A. That's all. The moment external magnetic field is there are various possible transitions are coming into the play because of hyperfine splitting. Okay. So why not electron directly jump from all the way very top to the bottom? Why not? It's like there are some transitions which are not emitting energy emitting transitions. They may emit in such a way of heat to the surrounding. So that's why the dotted lines, what I showed here, the red dotted lines, they may be not radiative transitions. Radiative transitions are solid lines, either green or red solid lines. Okay. Now you see, whenever there's a splitting, hyperfine splitting, if I introduce a green light onto the system, it will accept, means absorb the green light, and it will emit the red light. So, in a way, it becomes a nice strategy for us to know whether the external magnetic field is acted on the NV center or not just by incidenting the green light. If the red light comes out, then we can say, yes, there is a hyperfine splitting. If whatever is the green light is incident, it comes as it is without being absorbed by the system. In that case, you can say 532 nanometer never close to 1042 nanometer of the existing initial transition state. So 532 nanometer never going to be absorbed by initial transition if the system is existing in initial transition without any external magnetic field. Okay, so this is the idea people started to realize the external magnetic field presence. Okay, so how many transitions we are seeing, how many NV centers are responding. Okay, right? By counting the NV centers, people were able to realize exact the external magnetic field configuration. Okay, right? So let's see what I have for you here. See, 532 nanometer color is incident. Okay, and if I see a different red color, means it might have experiencing external magnetic field. Due to that, I am going to see the red color change. If there is no color change, means probably the external magnetic field is not there. That is what you can understand. Okay, what I have here, yes. So the way the structure is of the NV center sensors would be something like this. Okay, so they prepare a probe such a way, so small probe, only few NV centers are there at the edge of the probes. Okay, so those probes, if we bring near to the some magnetic field inducing surface, see the NV center would respond to that the surface of various magnets, and it changes its state. The change in the state in the form of hyperfine splitting. The moment hyperfine splitting is there, you incident a green light, you see a red light emitting out of the system. So how much red light is being emitted? In that way, we can count the press, like you can create the configuration of the magnetic field surface. Okay. So coming back to our discussion for today, that is NV defects, diamond defects. Okay. Yeah. So the structure, the band structure was shown here. Okay, which we saw earlier in terms of individual states. Okay, at the ground state as well as the excited state, you see. Okay, so if I have to understand more in detail, okay, so what should I do? I have to come up with the description of Hamiltonian. Okay, so the description of Hamiltonian will be there. It's consisting of the NV center and its surrounding. Okay, so the magnetic field of external magnetic field B is there. S stands for magnetic field of nitrogen and magnetic field of the vacancy part of the electron, let's say, right? So, and there is some kind of a electric field coupling. All those things are actually involved in this case. Okay, right? So, by default, there is some splitting will be there, 2.87 gigahertz. Whenever external magnetic field is there, that is going to create a Zeeman splitting in the system. Means hyperfine splitting will take place for level A and level E also. Means ground state and excited state gets split. Okay. So optically you can measure by what? You can incident 532 nanometer light. Okay. And you will be looking for the emission at 637 nanometer, red color. Okay. So the moment you see such a change, what you say? Optically detected magnetic resonance, ODMR spectrum. Okay. So depending on the ODMR spectrum, you can calculate what was the magnetic field creating that particular hyperfine splitting. Okay. So you can go on to come up with creating not just probing, not just sensing a magnetic field. If you want to create some kind of a qubit out of it, okay, a memory out of it, quantum qubit out of it. For that, what should I do? We can use something called coherent spin control, and we can make the system to oscillate between what were the states? Okay, 1 minute. The states were, for example, NV0, NV negative. The system can oscillate between such states. Okay, I can see from the nuclear spin up and down spin. Similarly, electron can be up and down spin, right? Or the charge state of a qubit being oscillating between NV0 to NV minus. Okay, so using some coherent spin control, we can make the system to oscillate. So the ground state, as usual, will represent a 0 kit, excited state, and a 1 kit. Okay, so here you can use a pulse, pi pulse, to create a NOT gate operation, means flipping 0 to 1, 1 to 0, and pi by 2 pulse to create Hadamard gate operation. Right? So probably we might have discussed some time back, might have done it. So if the quantum state is in the ground by nature, the electron is in the ground, we can send one photon of energy exactly makes the transition frequency. So electron will jump and stays there for 1 microsecond. After 1 microsecond, we can send one more photon. In that way, we can create a hopping between continuously sending 1 microsecond apart photons. So that would be a pulse of photons. Okay. So if you find the area of this pulse is pi by 2 radians. So this pi by 2 radians pulse is known for creating ground state electron to become superposition state with equal probability. Means it is a 50% chance to exist in any of the given state at any given point, which means it's like a fair coin being tossed. Okay, so that is what pi by 2 pulse would look like. For example, if the electron is in the ground, if I want to shift it to the excited state, simply sending one photon or pulses of photons where the pulse area, okay, this is a pulse envelope, pulse area, if it is a pi, okay, pi area pulse, that pulse is going to put what? Ground state electron to excited state, or let's say if the electron is in the excited state, it will put the electron from excited state to ground state. So this is what pi pulse. Why Mathematically, you can find the area of the pulse exactly equivalent to these values. Okay, that's why they're called pi pulse or pi by 2 pulse. Okay, and interestingly, on a block sphere, if you notice, okay, this is a block sphere for you. At any given point, any point on the surface will make an angle theta with the polar. So north pole is 0 ket, south pole is 1 ket, and quantum state psi will make theta, sorry, phi angle with x axis. Okay, quantum state usually represented as cos theta by 2, 0 ket, plus exponential I phi sin theta by 2, 1 ket. This is what quantum state is represented. Now, initially, let's say quantum state is in the north pole, which means the quantum state is making theta is equal to 0. Means it is existing on the north pole. Now I want to make theta to become pi because I have to rotate quantum state all the way from north to south. So how much angle I have to rotate? Pi angle I have to rotate. So electron is in the ground state. To go to the excited state, that is south pole in the block sphere, how much angle I should rotate? Pi angle. So interestingly, what kind of a pulse of energy is required? The pulse of energy required to transition from ground to excited state is, interestingly, the pulse envelope area is pi. So that is why it's called a pi area, pi pulse. And the earlier case, if the pulse area is pi by 2, what happens is on a block sphere, quantum state is initially from psi 0 to rotated to what? Theta is equal to pi by 2. Whenever theta is equal to pi by 2 means what? The quantum state may be pointed anywhere in the equatorial plane. It can be pointing along the y-axis, it can be pointing along the x-axis, or negative x, negative y. Not only those 4 points, it can be anywhere on the equatorial plane because theta equal to pi by 2. Any point on the equatorial circumference would refer to that point. So that's why that is a pi by 2 pulse. Okay. So coming back to here, you can realize the superposition state and you can create the pulses using some control incident light energy, and you can also create adding a phase to the system. What is a phase to the system is, let's say I have a quantum state pointing along the x-axis. What is that? Pointing along the x-axis is, quantum state pointing along the x-axis is 0 ket plus 1 ket divided by square root of equal superposition, where cos theta by 2 is 1 by square root of 2, sin theta by 2 is 1 by square root. Both are 1 by square root of. Now I want to make it to become 0 ket plus exponential I phi 1 ket divided by square root of. Okay. So initially, what is the phi value? Initially, phi value here is 0. I'm pointing along the x-axis. I want to point any other value. Let's say any general. I want to introduce extra phase between 0 ket and 1 ket. What should I do? I have to rotate the quantum system from x direction to any other direction on the equatorial plane. It can run between phi value 0 to 2 pi. Sorry, 0 to 2 pi. Any value. Specifically, let's say phi is equal to pi by 2. What is that? That would be 0 ket plus exponential I phi is cos phi plus I sin phi. Cos pi by 2 is 0. I into sin pi by 2 is 1. So I'll get I 1 ket divided by square root of 2. You see now, Rotating from x-axis to y-axis is adding a phase of pi by 2 angle. So that also can be created in this system using the phase gates. Okay. And you can have a composite pulses, combination of pulses, which can shift from particular direction to particular direction and also rotate the vectors in a particular equatorial plane. So that's what composite pulses, and you can shape those pulses as per the requirement. Okay, see here it is shown. If you want to move the system from one state to other state, how the pulses has to be introduced. Microwave pulses, by the way. Okay, so the coherent properties, the excitation lifetime is about milliseconds. The coherence lifetime from microseconds to milliseconds. Okay, so different materials I can choose. From there I can realize much larger uh, superposition lifetime, that is a coherence lifetime. Okay, so that is how NV centers can come in. Okay, and just to know whether the qubit is perfect or not, we can cross check DeVincenzo criteria, whether we can create a scalable qubit out of it. Are we able to realize initialization of the qubit properly and long coherence times are existing? Does it allow universal gate operations on the system? Is it allows for reading out? All those things you can check. Interestingly, the NV Center satisfies all of them. That's why it's a very good quantum qubit. Okay. But only thing is right now the scaling is slightly difficult. Solid state qubits, one qubit to other qubit. If say you created a solid state qubit scaled version of about 10 qubits, if I want to add one more qubit, it is not that straightforward. That's why the LCR based transpond qubits are more handy, or even the photonics qubits are more handy when it comes to scaling up. Okay. So this part we already touched, I think, NV centers for quantum sensing. Okay. And you can realize quantum networks, creating quantum nodes, that is memories, and then connecting them. So you can always cross check with the defects, NV center defects and silicon defects when it comes to qubits, how good they are when in terms of operation temperature, readout, and the lifetime. All those things you can cross check. Obviously, there are some challenges in each case. What are those challenges also you can understand. Okay. So that is about the defects in solid state material. So these are the only two things which we have touched to so far. There are other possibilities also there, but not much is being explored these days since these are doing the job. Yeah. And Bhavnaji is asking, all the gates are realized with just pulses. Of course, yes. If the system is responding to the optical energy, that is pulses, so we can realize the gates out of it. Okay. So yeah, a lot of text is being put up in my slides. Okay. So this is for the reference, but ideas I try to convey. What you can do as I share this PPTs, you are welcome to explore the text inside and you can understand. Okay, little more what is being discussed. Fine. So that's about from my side. I will stop at this point. Yeah, more or less all the questions I addressed. Yeah. Okay, I'll hand it over. Yeah. Yes, Prahlad ji was asking, you showed pi and pi by 2 pulse as a modulated wave. Yes, something of that kind. That's an easier way to understand. That's why I've shown in that way. So how do you create a pulse from that context? You can see. Are they same? What is 5 by 2? Okay, what is 5 by 2? It's like a area of the pulse. Okay, right? So if you just take, let's say there is a curve. If I want to find the area under the curve, Okay. So let's say this is y equal to x. Sorry, y equal to some function of x. So what I do, I run the integration from x is equal to 0 to some x is equal to a. Okay. So the area under this curve is some value will come. So when it comes to the pulse, the area is comes out to be pi radians or pi by 2 radians. So that is what I meant. Okay. Yeah. Any other questions? No. Fine. Thank you, everyone. Uh, I think this is my last session in this module. If there is anything, we will definitely, I'll get back to you people. So thank you very much.
Thank you, Aswad sir. So, yeah, you are very supportive. You must have dealt with all the queries. And I would say it is really not very glad that you are saying this is your last session. We hope to see you more. Maybe in the next lecture series, we will surely contact you.
Yes,
And
sir.
if there is any possibility in this series also, I will again contact you. Okay.
Yeah.
And it was really nice that you delivered 5 lectures in this course. Thank you so much, sir. Thank you for being with us, sparing your time and sharing your expertise.
Thank you.
Yeah. Thank you once again, sir.
Yes, sir. Okay, everyone. Happy learning. See you sometime
Yes.
in the future.
See you, sir.
Bye
Bye.
bye. Thank you, Manoj, sir.
Bye, sir. Bye.